So good evening to all. Today's the first speaker of this instructional school is Dr. Sourav. He is an associate professor in the Department of Mathematics, IIT Bombay. Dr. Sourav received PhD from IISc Bangalore in 2012. His broad areas of research are functional analysis, operator theory, and several complex variables. And he has written very well-known papers in reputed journals like Advances in Mathematics, Journal of Functional Analysis, Journal of Operator Theory, and Bulletin der Science Mathematics, Indiana University of Mathematics Journal, and Journal of Mathematical Analysis and Operator Theory. And with such a brief introduction, I request Dr. Sourav to start his lectures.
Yeah, thank you very much, Professor Aldo. Fantastic introduction, I would say. Anyway, so it's been a pleasure to be a part of this instructional school, and I'm really glad and happy that I am offered this opportunity to teach here. So let us start with the basic things. So we, the teachers, we have discussed among ourselves how to proceed. So I am requesting the audience to just bear with us, okay? If you find a little deviation, then what you are seeing over there in the website, okay, about the lecture material and the topics, there could be a little deviation. So please bear with us, okay? But eventually we will cover everything. Please don't worry. And the other thing is, if you find any difficulty at any stage of the lecture, please don't hesitate to stop me and ask me questions, okay? At any moment of the lecture, at any time, please stop me and ask me questions. And at the end, there will be a question answer session also. So let us start. So shall I share my screen?
Yes.
Just a second. So could you see my screen?
Yes, sir.
Thank you very much. So this is going to be lecture 1. So the previous semester ended here in mid of April. So I am long out of touch with this writing pad. So sometimes I will get slow. Please forgive me. Anyway, so I would like to begin with basic stuffs of points and topology so that we understand things. What are complex numbers? We all, since we are mathematicians, and we all have seen this set. So what is that? This is nothing but a collection of points like this, where we all know x, y come from real line, and this I is such a number, we have I square equal to -1. Okay, so we have this thing. So we are collecting all such x plus iy, where this x and y will come from the real line, and I is, for time being, you think it as a number that has, if you square it, we will have -1. So this is what is complex numbers. Now, if you just look at it as a set, what to do with it? Okay, given a set, say if you have a set, meaning a collection of objects, you cannot do anything with it unless you have some structure on that set. For example, if you just look at the set of complex numbers, right, like what I have written here, we all know that there are two algebraic operations that are defined on it. One is plus and another is dot. Okay, so they are algebraic operations. They are algebraic operations. defined on C. Okay. So if you have algebraic operations, we know that this C with this plus, we all know it forms a group. Okay. And also we know that this C, if you remove the 0 along with dot, this is also a group. So we all have, I guess, learned it in our undergrad. Okay. So needless to mention all of them. So on one hand, we have a couple of algebraic structures on this set C, and now we will have topological structure on C. So I'm going to define what is a topology. Anyway, we all know it perhaps, but we will have a brief brush up of our existing concepts. Okay. So whatever I have felt in my mathematical career is that we don't understand higher things, higher mathematics, most of us, just because we don't learn the basic concepts properly. We don't learn the definition. So that is what I felt. So this is the reason. Let us have a concrete build of topology, okay? Because this group theory is, I believe, is known to everyone. It's taught in undergrad colleges. Nevertheless, so once we have a topological structure on this set C, okay? So on one hand, we have a couple of algebraic structure, and on the other hand, we have a topological structure. So there must be an interrelation between these two. Okay, the algebraic operations and the topological structures. Okay, we will see it. Okay, so what do we do in mathematics? Given two sets, okay, you have one set here and you have another set there. Say, call them, say, X and Y. So if you have, this X is equipped with some algebraic structure and some topological structure. I'm going to define what is a topological structure. And same for Y. So then we can consider functions between them. We can study all possible functions between them which preserve those structures. What does it mean? If you have addition here, okay, then we want to find out whether a function preserves this addition, meaning f of, say, x1 plus x2, whether this is equal to fx1 plus fx2. Note that whether this thing happens. This plus, okay, this plus comes from x, and the other plus, it comes from y. This plus comes from y, and this plus comes from x. Whether this thing holds. Then we say that the algebraic operation plus is preserved. Okay, we are adding 2 points on the left hand side, and if we look at the images, it is equal to their individual sums. So this is what is called preservation of a structure. So in a similar fashion, you can talk about preservation of this dot structure, which we call multiplication. Okay, and we shall see if F preserves the topological structure. Okay, so this is how we study functions between two sets, where each set is equipped with several algebraic and topological structure. So later on, you will find there is another structure called manifold structure, okay, on these sets, so that you can talk about differentiability. Okay, if you have a topological structure, you can talk about continuity. We shall see that. If you have a manifold structure, you can talk about differentiability. Nevertheless, let us begin with the basic notion of topology. So what is a topology? So we begin with a non-empty set. So let X be a non-empty set. And let tau be a collection of subsets of X satisfying the following. Number one, the empty set. This is a subset of every set, we know that, and the whole set, they are there in the collection, number one. Number two is this is closed under any union, meaning you take any union of elements of tau belongs to tau. So, and number three, it is closed under finite intersection, meaning given any finitely many of them, their intersection is there. So, any finite if this collection tau, it satisfies these three properties, then we call that this tau is a topology on X. Okay. Then, as I said, we say that tau is a topology on X. And this X tau is a topological space. Okay, so you just remember three things. Phi and X is there, phi and X are there. So it's closed under an arbitrary union. You take any union of elements from it, it belongs there, and it is closed under finite intersection. It satisfies these three properties. Okay, so given two topologies on X, when we call one is smaller than the other or one is weaker than the other. So this is just a note. So given two topologies, tau 1 and tau 2 on X, we say that tau 1 is weaker than tau 2, or in other words, tau 2 is stronger or finer than tau 1 if you have this. If tau 1 is contained in tau 2, okay, we call this tau 2 to be finer than tau 1. Okay. And quite a few terminologies that we already know, and please don't get bored. Okay, please bear with us. So some of them are known, but we need a complete account. So we know what is a topology. Now, what is an open set? An open set is a member of a topology, nothing else. Okay, so if you have a topological space X tau, so if this is a topological space, then number one, a member of tau is called an open set. Okay. Number two, what is a closed set? A closed set is complement of an open set. A closed set in X tau is the complement of open set. Okay. So just for your information, whatever I am writing over here, I will save it as a PDF and I will send it to the instructors. Okay, to the organizers, so that you all get this as a note. So you just focus on the lecture. You can take note of it, but I will send it to you. Whatever I am writing here, I will save it as a PDF and I will send it to you. Anyway, so what does it mean? That means if G is open, meaning G belongs to tau, then G complement, what is that? That is X minus G is closed. Okay, and definitely conversely. Okay, meaning if you have a closed set, then its complement is open. If you just look at the definition. Okay. So these are definitions of open and closed set. And number three, what is?
Sir,
yes.
Sir, in the real number system, we studied the definition of open set, like a set is open if all the points are the interior point.
We will come to that. Please don't worry. Okay, we shall come to that. So this is the abstract setting where we are defining what is called an open set. But what you are saying is correct, absolutely correct, and we shall come to that. How these two notions are equivalent.
Yes,
okay?
yes.
They are the same thing actually. We shall see that. Yeah, but whatever you are saying is absolutely correct. Yes. So now I am going to define what is interior. So these definitions are in the abstract setting, meaning if you have a topological space, then what is an open set? This is an open set. Okay. So the point is that if we specify some topologies, we shall come to that. For example, when we shall discuss about metric spaces, there are special forms of open sets and closed sets. We shall see that. Okay. So what is the interior of a set? The interior of any set in X is the largest open set contained in that set. What is that? Just write the interior of a set E subset of X is the largest open set contained in the indeed you have, we define, we denote it by E interior. So this is the notation for interior. What is that? This is actually the union of all open sets which are contained inside E. So this is just needless to mention. You can see it clearly. This is actually equal to the union of all G belongs to tau. G is contained in E. So this is what is called the interior of a set. That is the largest open set contained in E. Okay, and what is that? That is actually the union of all open sets contained in E. We shall see later, we shall define what is an interior point, and we shall see that this interior is nothing but the collection of all interior points. We shall see that later. And what is the closure? The closure of a set is the smallest closed set containing the set. The closure of a set is the smallest closed set containing E. See the difference. Here the largest open set contained in E, and this is the smallest closed set that contains the set E. Okay, so we use this notation for closure. So this is actually the intersection of all F subset of X, such that F is closed and this E is a subset of F. So you can easily verify that. No, this is the smallest closed set that contains the given set. Okay.
Sir.
Yes, please.
From the fourth point, can we say that the arbitrary intersection of closed set is closed from the definition of closure?
Yes, that is true. Arbitrary union of open sets is open and arbitrary intersection of closed sets is closed. Okay. Anyway, I was just going to mention that. Nevertheless, so I will state quite a few facts that are very trivial, very elementary, but I am not going to prove them. They are just simple set theory. So I request you guys to take them as homeworks. So you will find it, and yeah. So this is one of the facts that is mentioned by someone. I was going to state that anyway. Any intersection of closed sets in a topological space X tau is closed. Okay, please verify this. It follows directly from the fact that any union of open sets is open. Okay, you take an arbitrary collection of closed sets and take its intersection and show that it is again closed. You use the fact that arbitrary union of open sets is open, nothing else. Only this fact will be used. Anyway, you are going to see all these things in the assignment. So you just better be prepared so that it becomes easier for the teaching assistant, okay? And this basic topology, this is all fun. It's not difficult at all. It's just basic set theory, nothing else, okay? What is a subspace topology? I am going to give you some examples, definitely. So just hold for a second. I have I'm sorry for the interruption. Anyway, so let us see some examples, some basic examples, so that you get the things very clear. So if you take, say, X is any non-empty set, and you choose tau to be its, what is meant by the power set, right? It's the collection of all subsets of X, okay? Then one can easily verify that this is a topological space, is a topological space. Why? You need to have, this tau to be closed under arbitrary union and finite intersection. Nevertheless, the empty set and the whole set are there because it collects all the subsets of X. Okay, so it's not necessary to mention that it is closed under any union of sets inside it, and it is closed under any finite intersection, right? It contains indeed all the sets. So this topology is somewhat, kind of a trivial topology. This is what is called the discrete topology. Okay, discrete topology means all sets are open sets here. You see, this tau contains all the subsets, so all sets are open here. Okay, so all subsets of X are open here. Okay, this topology is called the discrete topology. On X. So you can form a discrete topology on any non-empty set. You just collect all its subsets, okay, and call it a topology. As simple as that. Okay, a different example. If you choose X to be a two-point set, say it contains two elements A and B, and if you choose tau to be, say, phi A and X itself. Note that, phi and X, the empty set and the whole set, they have to be there in the topology, right? Otherwise, it is not a topology. So I am collecting these three. Now the question is whether this is a topology. Can anybody tell me whether this is a topology? Is
Yes,
it closed under?
Yes, sir.
Yeah, it is closed under any union, right? It is closed under any union and it is closed under finite intersection. Nevertheless, only finitely many are there. So then this is a topology. Then X tau is a topological space.
Sir,
So
I have a
results,
question.
yeah, please.
Sir, in the point one, you have mentioned the discrete topology. So I
Yes.
want to know if there is some significance behind that kind of nomenclature of discrete topology.
You mean what is the importance of this topology, discrete topology?
No, why it
That,
is named as discrete? Or
okay, the thing is that, why is it called discrete? Well, definitely there is a reason. If you look at X, if X is a non-empty set, and if you collect all its subsets, okay, I am going to define something called base for a topology. Okay, so a base for a topology is a sub-collection from the topology. Okay, such that, given any open set, you can find out a member from that sub-collection over there. I'm going to tell it in detail. So you will see that if we look at the discrete topology, then all one-point sets are open. And if you say all one-point sets, how do they look like? They're scattered, right? If you take two one-point sets in any space, they are two distinct points, right? They are scattered from one to another. So this is the reason, perhaps, I guess, behind this discreteness. Okay, all one-point sets are open here. We shall see that. Anyway, all sets are open here, but all one-point sets, they will form a base. Okay, we will see that in few moments. So this is another topological space, and we shall see examples of Euclidean spaces. For example, real line with Euclidean topology. We shall come to it in detail. I'm just writing here, but we shall study them in detail later. The real line with the Euclidean topology. So whatever we have learned in real analysis, that is what is called Euclidean topology. Okay. So the open intervals are open sets there. We shall see that anyway. So that is another example. Now I am going to tell you what is a subspace topology. So that is important because whenever we study a topological space, we shall consider, I am briefly describing the notion of topology here, and I will mention all those facts only which are necessary for the rest of the course. I'm not going to go into details of all things, nevertheless. So what is a subspace topology? So you have a topological space X tau. Okay, this is a topological space, and you have Y to be a subset of X. Okay, now if you form a collection tau Y that consists of this kind of sets, Y intersection G, where G comes from the topology. Meaning, what we are doing is the following. We are considering all open sets, meaning all members of tau, and we are taking their intersection with the given subset. This collection, one can verify easily. One can verify easily that this Y, tau Y, is a topological space. Okay, please verify this. There is nothing to verify at all. It contains Y. Why does it contain Y? It has to contain phi and Y, right? Why does it contain Y? If you want to get back Y from this collection, what G would you choose?
X itself.
X itself. Yeah.
Yes, exactly, X itself. So one can easily verify that it's a topological space. And this topological space, it's called, it's equipped with the subspace topology. This is what is called subspace topology on Y, induced by the original topological space X tau. Okay. So I am going to tell you a few properties of the interior and the closure. So what is the interior of a set? That is the maximal open set contained inside that set, right? That is the maximum, that is the union actually of all open sets contained in Y. So you can call it Theorem 1. Once again, these stuffs are extremely easy, and just set theory and you can verify this. So I am not going to prove them. I request you to prove it. So let us have topological space. And let A be a subset of X. Then we have the following. Number one, if we talk about A interior, it itself is a set, right? A interior itself is a set. And what is the interior of it? This is precisely A interior. Okay, please verify this. Number two is, if you take two sets and take their intersection, interior is given by so what happens with union? I'm going to ask you this question. Okay, what happens if you take A union B and its interior? Is it A interior union B interior? Okay, so you just verify this. Okay, X interior is X. And number four, G subset of X is open. G is an open subset if and only if this is equal to its interior. Okay, so you just find out a proof. So I just give it as a homework. And the question that I ask, I'm just writing down. So is A union B interior is equal to A interior union B interior? Always. Okay.
No, sir. No, that is false. It is not true in general.
Can you give me an example?
Yes, we can take A is equal to closed interval 0, 1 and B is
equal to closed interval 0, 1. You're talking about the real line with Euclidean topology, right?
Yes, sir.
So X is the real line with Euclidean topology. Okay.
B is equal to closed interval 1, 2.
Closed interval
1, 2.
Okay.
1, 2.
Okay. Then what is A union B?
A union will be closed interval 0 to 2.
Closed interval 0 to, yes.
Its interior will be open interval 0 to.
Its interior is open interval 0 to, very good.
And A interior union B interior will be open interval 0, 1 union open interval 1, 2.
This is fantastic. So this point 1 is missing, right? So very good. So this means we are missing one point. Thus, A union B interior is not equal to A interior union B interior, as one belongs to this but one does not belong there on the other. Okay, so the answer is no. So the answer is a no. Thank you very much. Okay. And what happens with the closure? You have a similar theorem for the closure, right? So what should be the analog of this theorem for the closure? Who can tell me? There should be an analog for the closure, right? A similar theorem for closure. Okay, let us see. I guess you all can guess it. So call it Theorem 2. Once again, we are in the usual setting. We have a topological space. And we have a subset. Then what do we have? Number one, what happens with E closure? Its closure. This is precisely equal to E closure. Number two, here you have A union B closure is equal to A closure union B closure. So if I ask you the same question, does it hold for intersection A intersection B closure? Is it equal to A closure intersection B closure? The answer will be again no. The answer will be again no. Just you imitate whatever you have done above. Okay. In case of interior, the answer will be again no. So what is the closure of phi? The empty set, it is again phi. And number four, a set is closed if and only if it is equal to its closure. So why have I written E here? I should have written B, sorry. Just a second. I should have written B here. B is closed in X if and only if this is equal to its closure. So again, you just prove it using simple set theory. You just take it as a homework. Okay.
Sir,
Now,
above question.
Yes, any question?
No, sir, for the above
If you have any
it is
question,
that
please tell me.
Yeah,
No, I can't hear you.
Sir, can you hear me now?
So, your voice is not coming properly. Can you just raise your voice level? I mean the voice level, the level of your audio in your computer.
So is it audible now?
Somehow I can't hear you properly.
Yeah, please ask the question, Monish Gupta. So if we can put the question to the speaker.
Oh, so I'm just saying for the above question we can write union of interiors is contained in the interior of the union. We can make that point.
No, that will come later. That will the speaker will explain.
No,
Okay.
I did not get the question. Professor
Yeah.
Allu, please
Yeah,
explain to me the question.
So she's asking that that union union of these interiors. Am I right, Manushi Gupta?
Yes, sir. Yes, sir.
Please repeat your question. It's
Sir, I'm saying union of interiors is contained in the interior of the union.
that is sure, but only equality case he is telling. So what she is saying that A union B interior is subset of A interior union B interior.
No, it's a superset actually. It's the other way.
Yeah.
Yeah. What she is saying is correct actually. Yeah, but here we are talking about just equalities. Okay. Yeah, thank you, Manushi. That's a nice question. So yeah. So now I am coming to the point. Whether I am coming to the point of defining interior point and limit point. So now I come to the point where it will coincide with your prior knowledge. Okay. So again, we have a topological space, and let A subset of X. Then number one, a point X from A. You just make a note of this. This point belongs to A. Okay, is called an interior point of A if there exists an open set U. Okay, such that you have this. Did you get this point? So what is an interior point? First of all, the point has to belong to A. That is point number one. You just make a note of it. The point belongs to the set. This is called an interior point of that set. If you can find out an open set U between this point and the set. So this point is given X and the set A is given. You can find out an open set that will lie in between X and A. Okay, this is what is called an interior point. There exists such an open set. Okay, and number two, point X belongs to X. Here it does not, it may not belong to A itself. Note that X belongs to X is called limit point. Or sometimes it's called an accumulation point. It's called an accumulation point if every open set U containing X intersects the set E at a point other than X. What does it mean? You see, first of all, when we talk about a limit point or an accumulation point, okay, so this is something that may not belong to the set itself. Accumulation point of A. It may not belong to A. And how does it define? It is defined in the way that if you take any open set, here in case of interior point, there exists an open set. Okay? And here it happens for every open set. If you have any open set U that contains X, that open set U must intersect A at a point other than X. Okay? So we have this, right? X belongs to U and U intersection A. Okay. Contains Y such that X is not equal to Y. So this is what we have for every open set that contains X. Okay. So this is what is called a limit point. Now I am going to state another theorem. As I said, you know what is the definition of an open set and closed set, okay, in terms of topology. Like any member of the topology is an open set, and a closed set is nothing but the complement of an open set. So now we are going to define the open set and closed set in terms of the interior points and the limit points. Okay. So what is an open set? An open set is something that is equal to its interior. Anyway, I'm going to state it as a theorem, but once again, this is this is just an easy theorem, and you can easily write down a proof using basic set theory. I think this is Theorem 3, if I'm not wrong. So a set E in a topological space so if I don't mention anything, this X tau will denote a topological space, is open if and only if all points of E are interior points. Okay, so we know the definition of open set. As I said, it's a member of the topology, nothing else. Now, here the claim is that a set is open if and only if any point of it is an interior point of it. Now, these two notions are equivalent. This is the content of this theorem. I request you to prove this theorem. It just takes, if you just look at the definition of open set, okay, in terms of topology, it's just a matter of time, nothing else. If you cannot prove it, just let me know tomorrow. I'll just prove it for you. Okay. So a set F in X is closed if and only if contains all its limit points. If once again, I just leave the proof to you. If you cannot prove it, just tell me tomorrow, okay? I'll prove it for you. But, anybody can prove this. Anybody with basic knowledge of set theory can prove it. Yeah. So now I am going to give you some examples, and I'm going to ask you what are open sets and what are closed sets, and what is an interior point and what are, So if you just have your prior knowledge of real analysis, you choose X to be the real line and tau to be the Euclidean topology. This ED means Euclidean topology, okay? So this is the Euclidean topology. We all are familiar about this topology, right? The open intervals are open sets there, okay? And the union of open intervals, you know that. So if you talk about this topology, okay, then please tell me what are the interior points of this set. If you choose A to B, say this set 1 by n, all natural numbers n union with the 0, the singleton set 0. Okay, can you please tell me what are the interior points of this set?
Sir, empty set.
Empty set.
Yes, so its interior is the empty set. And what are the limit points of this set?
Sir, 0.
Singleton 0.
Singleton 0.
Yes. Yes. So A closure is A, and it contains 0, right? So when do you say a set is closed? We have seen above. A set is closed even only if it contains all its limit points, right? So if we use this result, then we can say that it is a closed set, and so A closure is A, because A closure is what? A closure is what? The minimal closed set that contains A. That's what we have learned, right? What is the closure of a set? That is the minimal closed set. That is the intersection of all closed sets containing A. And here it is A itself. Okay? Yeah. So if we talk about some other set, say if we choose this X to be, say, the set of natural numbers, okay? And this tau is tau d. What is tau d? That is the discrete topology. Now tell me, what are the interior points of this set? If you choose A to be, say, the set of all even integers.
Sir, A itself.
You are saying all points are interior points?
Yes, sir.
And why is that?
Because in discrete topology, every subset is open as well as closed.
Yes. So A is open here.
Yes.
Since every subset is open, so A is open. And if A is open, it is equal to its interior. That's what we have learned, right? If we just go back, yeah, what he is saying is absolutely correct. If we just go back, G is open if and only if this is equal to its interior. And what is the interior? What is the interior? That is the largest open set contained in it. Okay? And if you just look at the interior of interior is the set itself. Okay? So it follows from this result that if you choose this set A, in fact, you can choose any subset. All points are interior points, right? So then its interior is A, and what is the closure?
Same set A.
Why?
Because every set is open as well as closed in discrete topology.
Yes, because its complement is, if you say, if you call it open, then just look at its complement. Its complement is also open because it contains all the sets, and the complement is closed itself. So every set is open and closed, indeed. Yes. So you have some knowledge about the interior and the closure. So what are the limit points of this set? What are the limit points of limit points of, this set, say union with, say, what are the limit points of this set?
Sir, in which topology?
Euclidean topology, definitely.
Oh, okay.
Sir, it will be closed interval 0, 5 union closed interval 6 to 8.
Yes. So you know what are the limit points. This is closed interval 0, 5 union. Okay. Now we are going to define a base for topology. So again, this is something that is important. That is an important concept. So that this be a topological space. And let you have a subcollection B from tau. So B is a subset of tau. Then this script B is said to be a base for the topology tau if for any open set G and for any P belongs to G, you can find out a member of this collection. So what does it mean? So if you choose any member from tau, meaning if you choose any open set G and any point from G, sorry, it should be P. You can find out a member of this subcollection that lie in between P and G. Okay. So if you just look at the definition of base for a topology, okay, it's a subcollection. It's a collection of open sets itself, maybe a smaller collection. Okay. So what is a natural basis for a topology? If a topology is given, and if you choose this script B to be tau itself, then it is naturally a basis, right? There is nothing to prove at all. So tau itself is a basis, always. So there is no beauty in that because it is the whole collection. Now the beauty lies in just minimizing it. So it's just a note. Tau is a base. This is always true. We know that. So how does it look like? If you have a point P, then P belongs to G subset of G. So meaning you have an open set G, you have something smaller inside it so that the point P lies in between. So this is what is called a base. This is what is called a base. Okay. Now, how can you recover the topology if a base is given? That is a question. If you just look at this collection, it's a subcollection of tau number 1, and and given any open set, you have a member that is smaller than that. Okay, given any open set G, you can find out a smaller member B from the subcollection. This is what is actually a base. So if we know the base, if it is given, the topology is not given. Say you have a set X and this script B is given, say. So it is declared to be the base. Script B is a collection of subsets of X. So what is B? B is a subset of power set of X, and it is declared that this is base for some topology. Now, how can we determine the topology? So, if we know a base, there is a topology that it generates. And how does it generate? You choose all possible unions. You choose all possible unions from the members of the script B. That will be a topology. Okay. You just take all possible union of members of beta, then you can verify that it actually is a topology. So that is the topology that is generated by this base. That's what we say. Okay. So if we just look at the real line, for example, if we look at the real line with Euclidean topology, the Euclidean topology, okay, then what can you say about its base? We all know that if we collect all open intervals, if we collect all open intervals AB, such that and A less than B, then it forms a base, right? So this is a base for this topology. Okay, because we all know that given any open set in real line and given a point, why? Because if G subset of R, here the Euclidean topology is open, then we know any X belongs to G, you can find out an open interval, say call it AX BX, such that sorry. So this is what we have learned in our real analysis, right? So this is a basis, and if you just look at this collection is much smaller than the collection of all open sets, right? Because if you just look at the collection of all open sets, they contain members like this, they contains member like say infinity. So this is open, but it is not there in this collection. Okay, so you understand, a base could be smaller than this, the original topology. The original topology always is a base, but this is something smaller. Can you make it more smaller? So once again, the real charm is if you cut down some more sets and find out a thinner set, which will be a base, right? So can you find out a thinner base for the Euclidean topology on R? Something smaller than this collection?
Belongs to rational number?
Yes, exactly. So that is a smaller collection. Thank you. So if you collect this set, call it B1, and collect AB, where this A and B will come from the set of rational numbers, okay, and A less than B, then this is also a base. And we have that this B1 is properly contained in B, okay? Because, given any open set, you can find out a member from this collection. You can find out an open interval with rational endpoints such that this thing will happen, right? And what is, well, I'm going to state a theorem, so that will give you a criteria for a collection to become a base. But that is, once again, very trivial. You can understand this very clearly. Nevertheless, I'm going to state it. I guess this is Theorem 4, if I'm not mistaken. So collection B is a base for a topological space, a base for a topology and a base for a topological space. They are the same things if and only if two things happen. Is X is union of all members if it belongs to this collection, and number two is whenever you have two members from the collection and you have a point from beyond intersection B2, there exists third member B3 from the same collection such that this B3 will lie in between X and B1 intersection B2. So you can easily verify this. Okay, you know the definition of this. Again, the proof is elementary, and I am not going to write a proof. You just take it as a homework. And I guess you can do it very easily. Yes, any question?
Sir, I think it will be P instead of X.
Instead of X, it is P.
Oh, thank you very much. Once again, messing up. Yeah, thank you. So, what is a subbase? That is another notion. What is a subbase? Subbase is a collection. It is such a collection, if you take all possible finite intersections from this collection, that will form a base. A subbase is a collection of sets from tau itself such that the collection of all finite intersections of members of it gives a base. Once again, as I said, if you know the base, you know the topology, right? If I give you a collection and declare that this is the base for a topology, how would you generate the topology? How would you get back the topology? You take all possible union of the members of that collection. That is the way to obtain the underlying topology, right? Or the topology that is generated by the base. Similarly, what is a subbase? A subbase is, once again, a collection from the topology. It's a collection of open sets. What kind of collection? If you choose to have all possible finite intersections of that collection, okay, all possible finite intersections of the members of that collection will give you a base. So, as I said, if you know the base, you know the topology. And once again, if you know the subbase, then also you know the topology. Because if you know the subbase, you know the base, and you know the topology, right? Once you know the base, then you know how to generate the topology by taking all possible union. Okay. So it's just a remark. If we know a base or a subbase, we know the topology. Okay. So if I give you a collection, if I give you this collection, for example, I am giving you this beta to be this collection AB cross. This is Cartesian product of two open intervals. Okay. So A, B, C, D, they are all real numbers, A less than B and C less than D. If I declare this, of course, this is a subcollection of the power set of R2, right? So if we talk about the power set of R2, then this beta is a subcollection of that, undoubtedly. We know what is R2, right? The Cartesian product of two real lines. Now, if you just look at this collection, and if I declare that, this is a base for some topology, what is the topology? If I declare that this is the base, so what is that? Cartesian product of two rectangle, Cartesian product of two open intervals. It looks like an open rectangle, right? It looks like an open rectangle in R2. So a rectangle without the boundary. This boundary is not there. This is not there. Okay? Because we have chosen the open intervals. So this is what we have in R2. If this is the origin, this is your x-axis and this is your y-axis. Okay. And if you have this to be your AB and this to be your CD, okay, then if you take their Cartesian product, you have such an open rectangle. Now, if you collect all such open rectangles, okay, then they will generate a topology. You just declare it to be base, and once you declare it to be a base, then how to get the topology? You choose to have all possible union, all unions, not just finite unions, okay, all possible unions of the members of script B, and call it a topology. You can see that it forms a topology. You can verify that, and that topology will be your usual Euclidean topology of R2. Okay, you can verify that. So then this is a base for the Euclidean topology on R2. Once again, please verify this, okay? So what are the things that you need to verify? You take all possible union of the members of it and declare it to be a topology and show that it is actually equal to tau ED. given any member from tau ed, you can find out something from here such that the point and the member in between that you can find out a set, okay, and vice versa. So this is what is the business of base and subbase. Now I'm going to define what is meant by a continuous map. Now we have enough machineries in our hand to define continuity. So let you have two topological spaces, say x, tau x, and y, tau y. Let there be two topological spaces, okay, and let you have f, a function from x to y. Okay. Then number one, f is said to be continuous if f inverse v is open in tau x for every open set on the right hand side. Number two, f is said to be continuous at a point. So what is that? Inverse image of an open set is an open set. This is what is continuity. So f is said to be continuous on the whole space X if choose any open set on the right hand side, and inverse image meaning what is f inverse v? So f inverse v is the set. So I don't claim that this function is invertible or bijective. This is just a notation. What does it mean? This means all such points x from x such that fx belongs to v. Okay. Now this is what is called continuity on a topological space. Now, how do you define continuity at a point? Like the way you have defined it in your real analysis. So f is said to be continuous at a point, say p belongs to x if or any open set v containing fx, there exists an open set u in x such that you have x belongs to u and f of u is contained in v. What does it mean? So this is your x and say this is your y, and you have a function f here, and p goes to f of p. You have an open set v containing it. Correspondingly, you can find out an open set u around p such that f of u is contained in v. So this is what is the condition for continuity at a point. That is what we have learned in your, we have all learned in our real analysis course, right? Now,
So that will be P belongs to you. That will be P belongs to you.
So change the point as X instead of P.
oh, once again, I'm sorry. Once again, this mishap. So this is P, P. Yeah, thank you. Now, this is your turn to prove that these two definitions agree with each other. What does it mean? We have defined continuity on the whole space X, and we have defined continuity at a point X, at a point P. Okay. Now, how do you combine them? You combine them by this result. Okay. Just call it a theorem or lemma. Better. Just call it a lemma. So f from X to Y is continuous. That means definition 1, right? Inverse image of open sets is open if and only if it is continuous at every point of X.
But
Muhammad, please. Muhammad Salah, please mute your mic.
Sir, mic off हुआ है sir. Your mic is off, sir.
My mic is off. Hello, can you hear me?
Yes, yes. Now we can hear.
Yes, we can.
Oh, I'm sorry. Somehow, there was a click. No, once again, So how to combine these two definitions, as I said. So f is continuous, meaning definition 1, inverse image of open sets is open, and it is continuous at every point, meaning it's continuous at a point, the definition 2. Okay? Given any point and any open set containing Fv, you can find out another open set U such that f of U is contained in V. So if is continuous, if and only if it is continuous at every point. So this combines these two definitions. So please verify it. So I am going to stop here today, and I will explain the rest of the topological stuffs, and I will introduce limit, the concept of limit, and limit of a sequence and convergence. Okay, the convergence is something that should be learned properly. If you know what is convergence, definitely I am going to introduce metric spaces in the next class. So if you learn the definition of convergence properly, then you can learn anything in analysis. That is what I believe. Okay. So today I am going to just stop here, and I will send you the notes. Okay. So any one of you do have any question, please feel free to ask me.
Yes, sir. I have one question.
Please.
Sir, for a given topology on any set X, how many bases are possible? And if all among possible bases, what is the relation?
It's very difficult to say how many bases are there. For example, if you just look at the real line with Euclidean topology, you can say this is a base, but you never know how many bases are there. At least I don't know. Okay. So, for example, if you just look at if you just look at the real line with discrete topology, for example, okay, then every 1 point set, if you collect all 1 point sets, it forms a base, okay? And any collection which is a super collection of that will also be a base. Do you get me? If you just look at, I come to your question. If you just look at R with tau d, that is the discrete topology. That means all sets are open. And now if you collect this B to B, okay, all singleton sets, X is a real number. Then this is a base. You agree with this, right? All 1 point sets, if you collect all of them, then it forms a base, right? Now, if you choose any super collection of that, if B1 is something, that lies in between B and tau d, meaning this B1 is a subcollection of tau d. It's a subcollection from the topology itself, and it's a superset of beta, script B, sorry. Then it is also a base. Then this is also a base. You can prove this easily, right? Because you are putting some more points. If you add some more points to a base, it is again a base. No doubt about this. Now, how many such members are there in between this script B and tau d? So you can never know how many of them are there.
It is true for every topology.
Yes, it is true for every topology. It is true for every topology. If you have
not
a base,
only for discrete case, it is true for every case.
Yeah, I am just talking about the number here. Okay, I am talking about this discrete topology to tell you about the number. Yes, you are very correct. The point is that this holds for any topology. One side you have the topology, and on the other side you have a base. If you put anything in between, that is again a base. If this is a base, then this is also a base.
Yes.
Okay.
I think this is a more appropriate question, that if X contains some points, then how many topologies are to be constructed over X? This could be a question, I think.
That is again, yeah, that is again a question, I understand. But again, the answer is not known. How many topologies? It depends upon the set. If you choose a finite set, then you can count the number, I guess.
Yes, actually, I am telling the case of finite one. So this maybe one can say that there are some topologies by counting.
Yeah. That is a point. That is a point. If you have a finite set X, say if you have X to be finitely many points, n points, meaning say without loss of generality, you can call it there's n points to be 1, 2 until n. Then how many topologies on X are there? That's what your question, right? Once again, the number will be finite definitely, but I don't know the exact number. It's a combinatorial thing. It's a combinatorial thing, but the number will be finite here.
Yes.
If you choose, Mr. Firoz, you have a question, right? Someone raised a hand.
Firoz Ahmad
Sir,
Bhat.
I have one question, sir.
Yes.
Please.
Hello. Sir, if we take like a set in a topological space, and we take every open set a set in a topological space, and if we take every open set contained in that and use containment partial order, then we can define closure by Jones lemma. Means we can prove that it has a maximal element. So why they are not defining like this? Why it is not needed to use Jones lemma for checking there exists a maximal element?
I did not get your question. Can you please repeat your question once again? I somehow Your voice is not coming properly.
So actually, if we take a set and all open set containing in it, a collection of all open set containing in it, and
so if you
define
one question, you are taking a set and then you are collecting all open sets in X without any structure. How can you collect all the collection of open sets?
No, I am talking about a in a topological space, a set is taken, and if we in a topological space, a set is taken. If we take a set and take collection of all open
X
sets.
is a topological space. This is your topological space, and you choose a set E subset of X. Okay.
Yes, sir. And if we take every collection of open set containing E.
Okay. So you choose G subset of E, and if this is your topological space,
it is a
you are
collection
saying
of
all open sets that are contained in E, right?
Yes, sir.
And G belongs to tau. So this is what you mean. This collection.
Yes, sir. Yes, sir.
Yes.
So then we can define partial order in this collection, sir.
You are going to define partial order.
Yes, sir.
Yeah.
Sir,
yes.
And by John's lemma, we can prove that it has a maximal element.
Okay. And what is that maximal element here? What is that maximal element here? Yes, that is the interior. Exactly.
So why they are not? Why every book says like it has a it is interior is the maximal element, and without proving this, so it is not needed, or they are just left that.
Yeah, the thing is that the interior is defined in terms of the union of all open sets, and that is logically valid. The point is that if you collect, as I said, if you have this collection, so this is a collection, right? This is a collection. If you call this, if you call this script F versus script G, if you call this collection script G, now I am taking the union of all G, where G comes from this collection. So this is what is called the interior of E, right? And this is a valid definition. This is a valid definition. You don't need any kind of John's lemma for this. You are collecting, you are defining a set. This set is well defined. The set, the way you have defined it is very nice. It is well defined. No doubt about this. And since a set is well defined, you can take union of all its members. That is also well defined. And you are declaring this. Yeah, you are declaring this to be the interior. You are declaring this to be the interior. And indeed, this is the largest open set that is contained in E. Nothing bigger can be there. Yeah, it follows from John's lemma. What you are saying?
Have to prove that, sir.
Yes.
Like,
you are correct. You are correct.
Maximal.
Yes, you are correct. You can apply John's lemma. Okay.
Yes.
But John's lemma can be applied to any collection of any collection of sets where you have this partial order relation in terms of the containment. One set is less than equal to another set if it is contained in that set. Okay.
Yes.
John's lemma can be applied. Yeah.
Yes.
Any other question, please?
Sir, there is one question.
Yeah, please.
Sir, what was the motivation to consider only 3 conditions to define the topology? That is arbitrary union and finite intersection and belongingness of phi and x. So is there any specific motivation for this?
No, the thing is that all things are focused towards having, initially when the topology was introduced, the focus was to get the Euclidean topology of the real line. That was the basic motivation. If we want to collect all open intervals in the real line, and if we take all possible unions of those open intervals, then it gives you a collection. And what are the properties that this collection does satisfy? That was the question. Okay. And making an analogy of it, okay, the mathematicians have defined the topology in abstract setting. As I said, if you collect all open intervals in the real line,
Yes.
And if you take the collection of all possible union from that collection, okay, then you can easily see that collection satisfies all three conditions of this definition of topology. Okay, all three axioms.
Yes, sir. Thank you very much, sir. Thank you.
Yeah. And Mr. Firoj, you were asking something.
Yes, sir. I have some humble submission. It's not a question, sir, just a kind of suggestion, sir. We have not taken any example from complex point of view since the course is going.
Yes. I am aware of that. I am going to define. Metric space in the next class. Okay.
Yes, sir.
And the Euclidean spaces are all metric spaces, right?
Yes, sir.
In particular, the set of complex numbers, if you talk about, this is same as R2 topologically.
Yes,
we
sir.
shall see this in the next class. Okay.
Okay, sir. Okay.
And we will find the representation of every complex number.
Yes, sir.
Yeah. Thank you.
Okay, sir. Okay. Thank you.
And any other points or question or suggestions?
Sir.
Yes.
Is there any difference between preposition, lemma, and theorem, sir?
That is a question that you ask Professor Allu. Professor Allu can answer this question. Professor Allu, are you there?
Yeah, I'm there. So maybe in the next course,
what is the difference?
Starts, I will explain them.
Difference between a proposition and the lemma and the theorem. That's a valid question, but I am directing these questions to Professor Allu because he is the senior most here. Okay.
No, we will come in the problem solving sessions. Let them learn first few topics, then we will go for the general discussion.
Yeah.
Thank you, Dr. Sourav. It's a very nice introduction of the topology.
So tomorrow, thank you. Tomorrow I am going to define metric space briefly, and metric space is a special kind of topological space. And from that, we will learn how to generate the Euclidean topology. The Euclidean topology is also metric topology. So we shall learn it tomorrow, along with what is meant by limit of a sequence and convergence. Okay. So that will build up the base for this course, the entire course, whatever is required. Anyway, so I'm going to stop sharing. And if there is no more question, then shall I give them it?
I would like to say that your handwriting is very much clear and fine. It is
thank you.
like, yeah.
Thank you.
And your lecture was very good. And I was thinking like it was computerized, not you were writing, not that writing, but it was like computerized. It was very much clear and fine.
Oh, thank you very much.
Yeah, and your lecture was actually very good. We enjoyed it very long.
Thank you.
Okay, sir. See you tomorrow.
Thank you, Sandeep Kaur. So let us thank the speaker once again for a very interesting lecture. So we'll meet again tomorrow at 5 o'clock.